Hello, it's Keith here, and this is lesson 4 of my PDP11 assembly programming tutorials. This time we're going to be looking at the stack. We're going to discuss what a stack is, just in case you've not come across assembly and the stacks before. We're going to look at how one works, how it works with calls, and we're also going to look at some more mathematical commands, ones relating to carries, and also the multiplication function of the PDP11. So quite a few things we're going to be looking at there. Now, I tend to assume you've probably know some assembly before if you're looking at PDP11, but just in case you don't, I'm going to discuss the concept of what a stack is and how it works. Now, a stack is a store for temporary data within our processor. Often when we're working with our program, we're going to need more registers than we've got. We might have a subroutine that needs its own set of registers, but we need to restore the original set when we're finished with that subroutine. And we use the stack to store temporarily registers that we will need back later. What happens is that the stack works kind of like an in tray. If we've got a register's value that we'll need later, we put that onto the stack, and then if we've got another value, we put that onto the stack as well. But when we take them off in the reverse order that we put them on, kind of like an in tray that fills up with paper, but it's always the last piece of paper that we put in that's the first we take out if we're taking out from the top. And that's how the stack works. And what we would do is we would push, say, register 1 onto the stack, and then push register 2 onto the stack, and then those two would be stored in that stack, and then we would take them off later on. Now, the stack on the PDP11 works down in memory, so the stack pointer points at the top part of the memory, and every time we push a word onto the stack, it will move down in memory and those items will be pushed on, and then when we take them off, we move back up in memory, back hopefully to the original starting point, assuming our program ends up with the place that it started. Okay, so that's the concept of a stack, a last in, first out stack, and also a just brief description of why we need them. It's just we don't have enough registers, we don't have an infinite number of registers, and we don't want to start allocating different memory addresses for temporary storage, because then we'd have to work out which ones were going to be reused when, or we would just have to start allocating huge amounts, whereas a stack, it will grow and disappear as our requirements change. So it's very flexible in that it allows us to have a large amount of memory for a short period of time, and then that will all disappear when we no longer need it. Let's go over to today's code and let's have a look. Now, there are no dedicated push and pop commands on the PDP11. Like a lot of other systems of this sort of caliber, we actually use the addressing modes. The auto pre-decrement and the auto post increment are actually our stack addressing modes. So when we move a value onto the stack pointer and we decrement the stack pointer, that is effectively a push command. And when we take an item from the stack pointer and then increment the stack pointer, that is effectively our pop command. Now, we are going to have to match these up because, as I say, the last item we put on is the first we take off. So what I always do in my code is I add extra tabs to note where the matching push and pop are, and the push and pop here. Now, of course, you could remove these tabs, but you might get confused as to what value you're getting back. And it's very important when you're using calls and returns, for a reason we'll see in a moment, that we match them up and we leave the subroutine with the stack pointer in the same situation it was at the start. And usually that would be by popping all of the items back off that we pushed on, or alternatively resetting the stack pointer in some other way. Okay, so what are we going to do here? Well, we're going to load some test values into our register R5, and we're going to push them onto the stack. First, we're going to load 1 and 5/7 in octal here onto R5. We're going to push that onto the stack, so that moves it into R5, decreasing the stack pointer by 2 because we're pushing a word on. Then we're going to load 1 and 5/6 into R5, and then we're going to move that onto the stack again, decrementing the stack pointer and then moving it onto the stack. And then after a few other tests here, we're going to restore those two values by popping them off the stack. Now, we've got this show stack command at each stage. That's going to show the state of the registers and also the stack itself. It's going to dump the memory that makes up the stack. So we're going to be able to see what the stack pointer is actually doing. Now, as an added bonus here, we're going to quickly discuss what a macro is. Now, this isn't a command within our assembler. This is a macro I've defined. You can see here I've defined macro.macro and the command show stack, and this is going to move the stack pointer into a temporary memory address and call this function here. Now, the reason I'm using a macro rather than a subroutine is the subroutines actually alter the stack. So I couldn't do that. It would have made things very difficult for me. So I've decided to do things this way instead. And I guess the ability of these macros is the reason that macro 11 is the name of our assembler. I'd say they're very powerful, actually, very good. So we're going to be using them at various points here, but we're not going to discuss them in any more detail at this stage. Anyway, let's fire up today's example on the R11 and let's see what happens. If I can just negotiate this around my screen a little bit. I'm going to struggle a little bit for screen space today, but we'll see what I can do. Okay, so what have we got here? Well, okay, so show stack is showing the contents of these registers and also this dump of memory just here. So this here is the starting point of our stack. You can see there's no interesting entries here, they're just all random data here. R5 has been loaded with our value here. And then we moved R5 onto the stack, and you can see that has happened just here. So that is the item we pushed onto the stack, R5. We also loaded R5 with a different value, 1 and then 5 6s, and you can see that represented here. But that's not yet onto the stack. We then moved that onto the stack as well, and we loaded 1 and 5 5s, and then showed a new line, and then showed the stack again. And you can see the state of that just here. The 1777 is on the stack here, at the top of the stack. Because it moves down every time there's a push done, the second item is just here below that, and you can see our stack pointer is actually going down each time. So our stack pointer would effectively be here, then it's here, and now it's pointing to here. Okay, and you can see R5 contains our 1 and then 5 5's value from just here. We then moved an item off the stack and showed the stack, and we got back the 1 and then 5 6's here into R5. And you can see that's actually vanished off the stack. Now that's not because the stack deletes items, it's because my other routines to show the contents of the stack are putting some other items on the stack. So they're corrupting everything below the position of the stack pointer when the show stack is being displayed. It's just an unfortunate limitation of the way I'm testing today. It's not that the items are by definition zeroed or wiped with random data. Now we've got our 1 and 5 6s back here. We then pop another item off the stack, that's this line just here, and we've now got our 1 and 5 7s back. So as I sort of said, we've got them back in reverse order. The 1 6 6 6 6 here is there, and then the 1 and 5 7s is just there. And as the stack went down here, it's gone up here, and it's ended up in the same position as it started, which is what we want to try and do. So of course, we can nest these as many times as we want. Yeah, we can have lots of different register items, and also we don't have to pop back into the same item as we pushed on. We can actually push R5 on and then pop R4 off. That will work just fine as well. We can actually also push byte values on if we wish. Now the only thing is on the PDP11, because this is a word-based system, if we try and push a byte onto the stack, you'll notice it's actually been padded out with zeros here. So we can work in bytes, but the way the stack pointer works will still work in words. Okay, so that's the basics of how we can use the stack. The next thing I want to discuss is how the calls use the stack. The way the calls use the stack is they actually push a register onto the stack. Now we've discussed this before. We're going to be in this case using the call and the return commands here, which will use the program counter. So what we're going to do here is we're going to call and we're going to run some nested routines, and we're going to see how these affect the stack, if I can figure out some kind of way of actually getting all of this on the screen at once, which is possibly going to be difficult. Okay, I've scaled my font down a little bit. Hopefully that will just about do. Okay, so what's actually happened here? Well, first of all, we've loaded 1 and 5 7s into R5 here. You can see that here, and you can see the starting position of the stack, which we showed just here. We then moved R5 onto the stack, and you can see that value just here. And then we've called a subroutine nest1, and that's just here. We've loaded 1 and 5 6s here, you can see that just here. And then next we've pushed that onto the stack here, and we've called nest2. And that's loaded 1 and 5 5s, you can see that just here. And then it's shown the stack again. Now you'll notice that the 1 and 5 7s is here, the 1 and 5 6s is here, but you'll notice we've got another value just here. And you'll notice it's suspiciously similar to the program counter here. It's just slightly higher, and the reason for that is that this is actually the return address of the subroutine. You see, when we do the call, we're actually pushing the program counter back onto the stack so that when we return, we know where to come back to within the code. That's the point that they're making here. Now, depending on the settings we use, we can use an alternate register as a return address with PDP11, but I'm not doing that here. But the thing I'm trying to say is that it's very important that we pop off everything that we pushed onto the stack back off the stack. You can see here's our most nested subroutine, and then as we're going back, we're popping the values back off the stack. and we're getting the original values back. Now if we don't, when we try and return, we will actually pop one of our pushed values onto the stack, and that will then become the return address, which is almost certainly going to cause a crash. Now if we're super clever, we can exploit that and use that as a tricky way of changing the address we return to. I have done that in some cases on Z80, but as I say, generally speaking, you're going to have a bad day, so to speak. So let's just try that. If I run this line out just here, we're now removing one of the pops so that we're not returning correctly anymore, and that just immediately closed. Let's see if UKNC will do anything a bit more visible. Okay, see what happens. Okay, well you can see here that's caused a crash, which is exactly what I would expect to happen. The reason is we've not popped that last value off the stack. That 1, 5 and 5 5s here has not been popped off the stack. So rather than this being our return address here, this has become our return address, which has caused an unsurprising crash. So if I just take this, put this back on and run again. Well, you can see now we've got the sort of results we'd expect. We're running the full program now. That's why it's very important to make sure we pop everything off the stack we push on, and that's why I like to use these tabs to make it nice and clear to me when I'm taking back an item that I put on before, and that helps me out and avoids me making too many mistakes, because often you'll find in your code, if you're getting crashes or very weird things happening, one of the first things you might want to think about is, well, is there any possibility I've actually corrupted my stack in some way, either because of a mismatch in pushes and pops, or in some cases because you're writing to the memory the stack physically uses. On my Spectrum Chibi Akamas, that was a problem. The screen memory and the stack memory are very close together, so if I accidentally drew something below the bottom of the screen, I would often corrupt my stack. So don't do that. It's something that is very easy to do. Okay, we're now going to look at using the carry to enhance our registers and simulate 32 bits. And this doesn't just work on 32 bits, it can actually work on much higher values. Now, whenever we do an addition of a register or a value, we're actually setting the flags as well. Now, the flag will effectively be the 17th bit, in quotes, the 17th bit of a 16-bit register. What I mean by that is if we add too much to a register and it overflows, then the carry flag will take whatever that 17th bit would have been. And we can use that with our add and subtract with carry commands to actually bring that extra bit into a second register. So we can use one register as the low half and another register adding or subtracting that carry as the second high half of a pair, and that allows us to simulate 32-bit functions. Of course, there's no reason why we need to stop at 32 bits if we want. We could extend that to 48, 64, whatever we want. And of course, we can do that even on 8-bit systems as well. So this is a common thing you have to do, especially on the 6502. So we're going to try this out here. If I just run this on the R11 here. Okay. Now, what have we done? Well, what we've done here is we've loaded R0 with a 0 here, and we've loaded R1 with a very high value here. Now, our pair here, R0 is the high word, and R1 is the low word. So this is a 32-bit pair, these two registers now. And what we're doing here is we're repeatedly adding 1 to R0, so you can see it's going up, and we're repeatedly adding the carry to R0 here, and that is effectively meaning that if R1 overflows, that carry bit, the 17th bit, is now being added to R0 here. And so you can see that when it overflows, R0 carries on. Now, in this case, R0 was just a very boring 0 here, but if we put a higher value in, of course, you'll notice that that is being retained. So you can see here, that's carried on as fine. And of course, if we change this to 11, well, as you would hopefully expect, when it overflows here, this becomes 12. So these are functioning as a 32-bit pair. Now, we're using add with carry here, but we can also do subtract with carry, and you can see here that we're able to reverse the exact same procedure and effectively subtract with a 32-bit pair here. Now, I believe that the PDP11 only allows add with carry and subtract with carry. You're not going to get multiply with carry or anything exciting like that. But as I say, this is, it's enough to get started with 32-bit numbers. And as I say, it's really essential with the 6502 that you do this for 16 bits. It's possibly not as necessary for your average programming with a 16-bit processor, but there's certainly impressive functionality that was worth mentioning. Okay, so that's our add and subtract with carry. Now the PDP11 actually offers multiply and divide commands, and we're going to be looking at those now. Now, if you're familiar with 8-bit systems like me, this is quite impressive really, and the PDP goes even further than that. Rather than just offering 16-bit functionality, it's actually able to work with 32-bit multiplication. What I mean by that is that we can multiply two registers together, and if the result is too high to be stored in a 16-bit register, we can actually use a pair of registers to have a full 32-bit value. So that's quite impressive. Okay, so let's have a look at that and let's learn how it works. Now, actually the same command does both 16-bit and 32-bit multiplication. The size of the result just depends on the registers we use. If we use an even numbered register, it will actually work as a 32-bit command. It will use a register and that register number plus 1 as the result. If we use an odd numbered register, it will just work in 16 bits. Now let's try that out now. So okay, let's fire this up and let's see what these commands are doing. Now in this case, what we're going to do is we're going to be multiplying R0 by R2 here. Now these are both even registers, so when we do this multiplication, the result is stored in not just R2, but R2 and R3, and R2 becomes the high part and R3 becomes the low part. Now you can see here we multiplied 2 by 3 here, and of course the result is 6. You can see it just here in this pair here. Now that's a very low value, but if we just change this, and if we change this to a much higher value here, for example, if I use much larger values like this when we do our multiplication, you can see that the result has been spread across R2 and R3 here, and that's because we were using a even numbered register as our destination R2 here. Now we can do the same with divide, and again it will work in 32 bits. If we do division with parameters R0 and R2 here, then what this will effectively do is it will set register R2 to the 32-bit pair R2 and R3 divided by R0, and the whole number value will be in R2 and the remainder will be in R3 here. Let's just fire that up and let's see that in action here. So if I just restore my values here, and if I run this again here, now you can see here that the result of our multiplication was 6 here. Now we then added 1 to this here, and then we did the division. Now we were dividing effectively 7 here by the value in R0, which is 2, and the result is of course 3 remainder 1, and you can see the 3 here, and you can see the remainder of 1 just here. Now we do have the option to do the multiplication at just the 16-bit level, and as I said before, it just depends on the parameters we use. So if we used even register numbers here, R0 and R2, then that's a 32-bit parameter, but if we use odd numbered registers, R1 and R3 here, well now we're just working at 16 bits. You can see that just here. Okay, so you can see here we've got our R2 and our R3, and you can see here that R3 has been set to 6, but R2 and R4 have been unchanged here. We're only now working at 16 bits rather than the original 32 bits. So that has worked just fine there. Now the problem is we can't do a division at 16 bits. We have to use a pair because otherwise we've got nowhere to store our remainder. So when we try and do it, you can see here we've actually had no effect here. So if we want to do division, we do have to use a pair of registers to achieve that successfully on the PDP11. So there we go. So we've had a look there at the stack and a variety of other mathematical commands that are quite powerful in the PDP11. We're getting pretty close to the end of the PDP11 programming tutorials, so hopefully we're starting to get a bit more confident with it. I hope you found this interesting. As I always say, if you have, please like and subscribe. Liking my videos helps YouTube be encouraged to recommend them to others, so maybe they'll find them and maybe they'll like them as well. But anyway, whatever you do, I hope you enjoy your programming and I hope you have some fun with PDP11. Thanks for watching today, and goodbye.